Hello Internet, welcome to Electromagnetic Field Theory tutorial series. Today I'm really excited to discuss the most sought after topic in EMFT, which is the Dell operator and its applications. Now, if you really want to study EMFT well, it is imperative to understand the Dell operator inside out comprehensively. Now, the Dell operator is one of the most logical and sensible things which you'll come across in EMFT, because it depicts the entire dynamism involved in the propagation of fields. And before I start with the discussion of Dell operator and the physical interpretation and meaning of the most common applications, which are gradient, divergence and curl of Dell operator, I'd like to mention a note that it is easier than, in fact a lot easier than what it is projected in a lot of textbooks and by a lot of teachers. And let us begin then. Now, Dell operator is depicted by this symbol, and mathematically it is equivalent to curly by curly x of one coordinate, curly by curly y of the other coordinate, and curly by curly z of the third coordinate. If you're working in XYZ coordinate system, then Dell operator is a representative of spatial change. As you could see, that Dell operator depicts the change of something in the x direction and in the y direction and in the z direction, which is rather not too difficult to understand, and anything on which Dell operator is applied would imply that that thing is surely moving in space and is changing its x, y and z coordinates, or is changing its position from one point in space to another point in the space. That being said, it has three very powerful, very important applications, which are gradient, divergence and curl. And the most amazing thing about these applications from a technical point of view is that simply the name of these applications would tell you the theology behind, or the rationale behind the application. Now I'll write down some mathematical expressions Now I've taken up some random scalar and vector quantities, and if we were to say them mathematically, how would you say it in a class, or how would you write them, and how would you interpret them? What is the correct way of saying them? So you would say that gradient of a scalar field is a vector field, or which is understood as multiplication of the del operator with a scalar field would result in a vector field. But mathematically you would say that gradient of a scalar field is a vector. That is how you would say it. And the next expression, you would say it as divergence of a vector field is a scalar. Now if we look at the expression itself, it is a dot product of two vectors. We know that del operator itself is a vector from these unit cap vectors. We know that del is a vector, so dot product of two vectors is a scalar quantity anyway. But it is said as the divergence of a vector field is a scalar, because we do not say that del dot f, or the dot product of del operator with some other vector, is a scalar. That wouldn't be as appropriate as saying that divergence of a vector is a scalar. Then we have the third application, which says that the curl of a vector is a vector, and understandably this is a cross product of two vectors, which will be a vector perpendicular to both these vectors, but we'd better say it as curl of a vector. Whenever del is acting as a constituent vector in a cross product, it changes the verbiage to curl of a vector, and it results in a vector which is understandable from the point of view of mathematics also. Now these were the expressions for the applications of a del operator, but what do they actually signify? What is the physical interpretation of these? So we'll try to interpret this. As I said a few minutes ago, that the beauty of the applications of del operator is that each of these applications can be understood by understanding the dictionary meaning of the words. Now the dictionary meaning of gradient is moving from one extreme to the other gradually. You would have seen gradient operation in Photoshop also, when an effect on a picture is applied from the point of view of changing its shade from darker to lighter as we go from one extreme to the other. So gradient is a slow change from one extreme to the other, extreme dark to extreme light. If you want to go from extreme light to extreme dark, will encounter an infinite change of shades. So the darkest shade will be on this side and the lightest will be on this side, and there'll be a gradual change that is known as gradient. And the best example to understand gradient of a scalar field is the example of temperature in a room. For example, if we have a closed room and the center of the room has hot temperature and the corners of the rooms have colder temperatures. Now we have this phenomena in hand. We create a scenario of a room where the center of the room is extremely hot and the corners of the rooms are extremely cold, and that will result in some kind of action to happen in the room. What do you think that action would be? Would there be some change in the temperature? Would there be dynamics involved in the flow of heat from one end to the other? The answer is yes. So whenever a situation is created like this, we have created a scalar field scenario of a hot temperature and a cold temperature that will result in the formation of a vector field that would be visualized as moving outwards. We'll see that the hotness will start to move right from the center of the room towards the outer areas of the room. And if we could see the flow of temperature change, we would definitely mark it as a vector field, because it has a direction, and that direction is the outwards direction. So you could say that the gradient of a temperature has created a vector field, which is the temperature change. And furthermore, you would see that the temperature change will be more towards the center of the room, and as we will encounter more temperature change here, the vector will be more prominent here at the center. But as it moves towards the edges of the room, it becomes lesser and lesser powerful. The temperature change will slow down. That is the gradual thing associated with gradient. Two things. The scalar field has resulted in a vector, and the vector, it originates with more power. It has more intensity when it is originating, and it diminishes as it approaches the penultimate point of its destination. So that is how gradient can be interpreted, or the physical interpretation can be thought of. Now next we talk about divergence. When we look at the dictionary meaning of divergence, it says opening up. Divergence is related to opening up of something in all the directions. and on the contrary, it is also related to its antonym, which is convergence. Convergence is making everything concentrate on one point. So divergence and convergence can be thought of as the opening up and closing up of something. That can be understood from the analogy of sun. Whenever we try to understand divergence, we take an example of a light source. For example, we have a spherical translucent ball. If we have a spherical translucent ball and we have an LED inside it, alright, we have a spherical ball, translucent, and we have an LED inside it. Now, the LED is going to emit photons, and those photons are going to be vector in nature. Please understand then, whenever a photon is radiated from an light emitting diode, it will have a particular direction in which it will go. There are many photons being radiated from the LED, but being a translucent ball, we really can't see the origin of those photons from the LED from outside. What do we see from outside is just the illumination. And what if we increase or decrease the intensity of radiation emission of the LED inside a translucent ball? We see that the ball starts to illuminate more, and the ball starts to diminish its illumination depending upon whether we turn the LED's intensity more or less. So this phenomena can be thought of as divergence of light. Light is a classical example of a vector. Light or a photon has a direction. It has its own speed, its own direction. But whenever a group of photons are radiated from an LED, of course they are radiated in different directions, but all of them are vectors. When a group of photons are made to diverge, they create a vector field which is known as illumination. So a classical example of divergence would be that divergence of photons, a vector field, is creating a scalar, which is illumination. What we see outside is a diverged illumination all across the surface of the ball, which is a scalar quantity. It doesn't have a direction. It is uniformly distributed on the sphere. So that could be thought of as the physical interpretation of divergence. And the physical interpretation of curl is even simpler. The physical interpretation of curl is understood from the flow of liquid inside a pipe, if we take a circular pipe and we make the water to flow inside the pipe, the motion of the water inside the pipe is circular in nature, or in other words, at any point in time, the flow of the water inside the pipe is tangential to the surface of the pipe. If water is moving in a circular direction along the inside surface of a pipe, that goes to show that water is always tangential to the surface of the pipe. So that is classified as a vector which is always remaining tangential to the pipe. And of course, this curl is being pushed forward, just like a drill, from the supply of the water from behind. But never at any point in time does the nature of water change, meaning it never leaves its basic nature of being tangential to the pipe. And what does it result in? That's the big question. The result is the movement of the fluid in the forward direction. What is the net result of the water being tangential to the pipe? If I say that water is curling around the pipe, what is the net result? The net result is the fluid flow inside the pipe, and that fluid flow will be perpendicular to the direction of the curl, and which is governed by the right hand thumb rule. If the water is curling clockwise, then you could easily find the direction of the fluid. If the water is curling like this, then the fluid will always flow in this direction, which is depicted by the thumb's direction. If the water is curling like this, the fluid will always flow in this direction. So that also seconds the very basic nature of the curl, that whenever a cross product of two vectors is taken, the resultant vector is perpendicular to both the vectors. So the curling of water is happening along the walls, and the direction of water flow is perpendicular to both the vectors, the curling of water and the del. So this will be the physical interpretation of the curl. So water remaining tangential to the surface results in another vector being created, which is the fluid flow perpendicular to it. And I hope with these classical examples and with the simple dictionary meanings of these words, gradient, divergence and curl, the technology has even making more sense, isn't it? And I hope this tutorial was helpful, though it was a lengthy tutorial, but I hope it was a help. And if you found this tutorial helpful, please consider subscribing to my channel and give this video a thumbs up. And you have a good day and a good life. Bye.